this lecture, we're going to be talking about H-infinity control. That is, how to control a system and reduce the H-infinity norm in the process. So we've looked at a number of other controllers, model-based controllers, the robust servo mechanism. Now we're going to look at H-infinity control. So as an introduction to H-infinity control, we're going to look at the motivation. We're going to look at a characterization of the bounded real property, how to achieve this using state feedback control, and then how to achieve this using output feedback control. So what is the motivation? Well, we have already seen that the H-infinity norm is an induced norm for finite energy signals, finite RMS signals, and finite power signals. So as an induced norm then, it has a clear ramification. So if we reduce the H-infinity norm, we reduce the input-output energy of the system. We reduce the input-output gain, RMS gain of the system, and the input-output power gain of the system. So what is a physical interpretation? Again, given a system, T, that is a function of some controller, for example, with input disturbance or noise or whatever signal that would be undesirable entering our system, and output, and Z being the output that we want to keep small with respect to such disturbances, then the H-infinity norm satisfies this inequality. And so the energy output is less than or equal to the H-infinity norm times the energy of the input. So the H-infinity norm then provides a bound on the energy throughput of the system. Now, in order to work with this, we work with something called the Bounded-Real Lemma. So if we're given a system of this form, so notice instead of having a BU and a y is equal to CX, we have GW, so W is our disturbance input, and HX. Notice that we don't have a D term here. We could have a D term, but as you've seen, the D term makes things a lot more complicated. So we'll start simple enough. This is complicated enough without the D term. The system is bounded real if and only if there exists a positive definite P that satisfies this linear matrix inequality. Okay, and so we're going to see that here in just a moment. In terms of being able to compute the H-infinity norm of a transfer function T, we have these following equivalent relationships. The infinity norm is less than some number gamma. Phi, notice this phi is not the state transition matrix. It's actually given by this quantity here. Phi of S is given by gamma squared I minus T transpose minus S T of S. So notice that this quantity here, is like the magnitude squared of the transfer function. And so gamma squared I minus the magnitude squared basically is saying that the magnitude squared of the transfer function is less than gamma squared. So if phi is positive. Phi is positive for all omega, for all real values of omega. So when S is equal to j omega. So remember, S equal j omega is the stability boundary for the system. So remember, if you have poles in the left half plane, all your poles are in the left half plane, the stability boundary is the imaginary axis. And so we're basically calculating this quantity along the imaginary axis. We've already seen the Hamiltonian matrix, and the matrix M gamma has no purely imaginary eigenvalues. And finally, there exists an X positive definite such that this linear matrix inequality is satisfied. And we just saw this linear matrix inequality. So we've seen it before, and so now we're seeing it again. So again, the Hamiltonian matrix is given by this expression. It's a 2n by 2n matrix. It involves A, G, and H, and gamma. It's a function of gamma. So for gamma positive, this matrix has a clear division of eigenvalues. To see that, we notice that if we do a similarity transformation on this matrix, remember, a similarity transformation does not change the eigenvalues. It just rearranges the states associated with that. So we can go through and show that this is equal to this, which is equal to this. So now what is this telling us? Oh, incidentally, the matrix J here is this matrix, 0i minus I and 0, and you can show that that matrix is equal to its negative inverse, its own negative inverse. So if I look at the eigenvalues of m gamma, those are the same as the eigenvalues of this quantity, which are the same as the eigenvalues of this quantity. Notice that the eigenvalues of m gamma are equal to the eigenvalues of that same matrix transpose. And so what this equation tells us is that the determinant of Si minus m gamma is equal to the determinant of Si plus m gamma. So what that means is I have what's called a symmetric spectrum. So we know that if A, G, and H and gamma are real values, then this matrix will have, in general, complex eigenvalues. What this is saying is, it is saying basically this, that this matrix will have eigenvalues that are symmetric with respect to both the real and the imaginary axes. The real and the imaginary axes. So if I have an eigenvalue here, I'm also going to have an eigenvalue that's a mirror image across the imaginary axis, but I'm also going to have a mirror image across the real axis. So I can think of there being like a rectangle having 4 eigenvalues. So notice here, this is a real eigenvalue, and it's going to have its symmetric, its mirror image over here. Being on the real axis means it's already symmetric with respect to the real axis. So whenever I have a complex eigenvalue, I'm going to actually have 4 complex eigenvalues associated with it in this matrix. Since the eigenvalues separate, we can separate the eigenspaces. So we can think of there being a stable eigenspace, that is an eigenspace associated with the stable eigenvalues, so that is the eigenvectors associated with the stable eigenvalues, and then an eigenspace associated with the unstable eigenvalues. So the Vs is the set of is a basis for the stable eigenvalues, and Vu is a basis for the unstable eigenvalues, and it satisfies. So this is going to be a square matrix, and so I could look at the diagonalization of m gamma. If I took this matrix inverse over on this side, I would get this diagonal matrix, or in general it may be a Jordan matrix. But lambda s is going to have it's going to be a triangular matrix or diagonal matrix, and the diagonal elements are all going to have negative real parts. Okay, negative real parts. The lambda u is going to have all positive real parts. So what difference does that make? Well, it turns out that we can use that to calculate something important. Okay, so if we partition the eigenvectors this way, so if we partition them in half this way, and use only the stable eigenvectors, assuming that this quantity is non-singular. This is going to be, remember, this is a 2n by 2n matrix, so that each of these submatrices is n by n. This is going to be a square matrix assuming it's non-singular, we can define this matrix P to be this quantity multiplied by the inverse of this quantity. So why would we want to do that? Well, hang with me. So remember, these eigenvalues, eigenvectors satisfy this relationship. Multiplying this equation on the right by VS1 inverse, so multiplying through, we get this relationship. And here I've stuck in a VS1 inverse times VS1, which is just an identity matrix. Okay, but now I'm going to multiply this through here, and call this quantity AC, and I have this relationship, I times P times AC. So we've seen this kind of relationship before. And what exactly does it mean? Well, it refers to the fact that we have a intertwining relationship, or an invariant subspace. So when we talked about invariant subspaces, we saw something like this before. And in this case, it's clear that the invariant subspace is such that AC has eigenvalues that are eigenvalues of M gamma, and in fact we know that. In fact, they're the eigenvalues associated with lambda s. They're stable eigenvalues. So in a sense, this is picking off the stable eigen. This is another set of basis vectors for the stable eigenspace. It's just a different set of coordinates. What does this buy us? So if I go through and multiply, this is M gamma IP times AC. If I multiply this out, I get two equations. I get these two equations. So if I plug this equation in for AC, this quantity in for AC, I can rewrite it and get this equation. So it's like, okay, what exactly is that buying us? Well, it turns out this equation has a particular name. It's called an algebraic Riccati equation, named after Count Riccati. And algebraic Riccati equations appear a lot in optimal control. So we will see algebraic Riccati equations a lot in EE552. Notice that as an equation, it's similar to Lyapunov equation. In fact, it's similar to the observability Gramian, but it has this extra term. Okay, and this extra term is actually quadratic in P. That is, it has P multiplying by itself in there. So basically, this quadratic matrix equation has many solutions, and these can be found to be given by various combinations of eigenvectors of M gamma. Now we have chosen a particular solution called the stabilizing solution. And we can go through and show that if we look at this quantity, A plus GKD, where KD is given by this expression, A plus GKD is going to be Hurwitz. How would we see that? Well, if we look back over here, AC, remember, is the stable set of is based on the stable set of eigenvalues, and so this is actually A plus GKD. So 1 over gamma squared G transpose P is KD, and so we see that here. And so A plus GKD is going to be Hurwitz. And that's what makes, so for this particular P that we have obtained using the stable eigenvectors, we get a KD, which is like a state feedback matrix, that makes this sum stable. And thus it is called a stabilizing solution of the Riccati equation. Again, there may be many solutions. There's only one. If a stabilizing solution exists, there is only one. Okay, and so we see that the ARE given by this expression, is related to the quadratic matrix inequality. So notice this is not a linear matrix inequality because it has has P appearing twice. So it's a quadratic matrix inequality. But we can go through and show that this quadratic matrix inequality can be given as a Schur complement of this matrix. So there's a transpose P plus PA, H transpose H. Those all appear in this term. And then we have these other things. And so this is satisfied if and only if gamma is positive. Actually, gamma is not 0. And the Schur complement is negative definite. Okay, so we have that relationship. We can also go and show that this relationship, we can go through and show that the same P that satisfies that relationship, we can, if we take this quantity and write it out, we get this expression. We can use this in this expression. So I have this quantity times this matrix times this quantity. So notice that this is the complex conjugate transpose or adjoint of this matrix. So I have this matrix, which is negative definite. So that's why I get this inequality here. And I can go through and show that when I multiply this all out, I get this expression. And this is negative. So this is what we called phi. And so we've basically gone through and shown that this is negative definite if and only if this is negative. This is positive definite. Okay, so that's the linear matrix inequality and the frequency domain inequality. So what's going on in the time domain with all of this? Well, if we consider this quadratic Lyapunov function, where P is the solution to the algebraic Riccati equation, the stabilizing solution, we can find a bound on the RMS gain of the system. So if we look at this quantity, gamma squared, if I go through and I take the derivative of this along the system trajectory, I will get this. We're going to use this to bound the RMS gain. So we want to have a bound like this. Okay, so what does that mean for us to do that? Well, if I look at the derivative along the system trajectory, this is what I get. And if, in fact, we have this being less than or equal to gamma squared times W transpose minus H transpose, X transpose, H transpose, HX. So this is Z transpose Z. Okay, so what is this giving us? What is all this giving us? If I go through and I look and if I take this inequality and expand it out, put everything on one side, I get this expression. I can factor this expression this way, and here's this matrix again. Boom. And so there's an X and a W that's associated with this that makes this inequality happen. And so we can see that there's a time domain interpretation. This matrix being negative definite means that there's an X and a W that makes this inequality happen. And in general, we may have strict inequality if X and W are both not 0. And what that does is that provides an upper bound on the RMS gain of the system. So not only is V dot in general negative definite, but it actually is less than the RMS gain. So by RMS gain, we mean gamma squared times the input minus Z transpose Z of the output. So that's the time domain interpretation of all of this. So we've looked at what it means for a system to have an H infinity norm and various ways of characterizing it. Now, how do we actually get a state feedback that does that? Well, stay tuned.